Greetings Internet, and welcome to episode 0 of what I hope will become a long series of badly edited videos discussing some topics in quantum physics, optics and electrodynamics. For now I'm calling this series Understanding My Research 101, or UMR 101 for short, and its continuation is subject to both the response this one gets and the amount of free time I can squeeze out of those weekends when I'm not doing my research. In this episode I will be addressing superposition. Well, what is superposition? Most people have heard the term in conjunction with Schrodinger's cat. It all started when an Austrian physicist and later Nobel laureate, Professor Erwin Schrödinger, or Schrödinger, proposed a thought experiment wherein a live cat is put inside a box containing a small flask of poisonous gas that is said to be released when a specific radioactive atom decays. The experiment involves placing the cat in the box, closing the lid, waiting for some set amount of time, and then asking questions about the cat's health before and after opening the lid. Well, is the cat alive or dead? Classically, this simple question has two possible answers, but a quantum mechanical theory of nature would state that before opening the box, the cat is really in a quantum superposition of both alive and dead. But as soon as the box is opened and someone takes a peek, the state of the cat collapses into one of the two possible options. But if the only way we can measure the cat's state is by opening the box and then looking, then how do we know which theory is the right one? Since the quantum theory seems to add some extraneous unmeasurable complications that don't seem to impact any measurement, shouldn't we Occam's razor it out and declare the universe to be classical? Well, not so fast. For the cat analogy to accurately portray quantum mechanics, there must exist some other measurements we can perform on the cat, the outcomes of which actually depend on the state of the superposition. Trouble with cats is that they are massive, and we'll get back to that later. To analyze this further, let's consider simple abstract objects with colorful properties, death not being one of them. Consider box, i.e. measurement device, that has two lights, red and blue, and it takes in a particle and flashes a particular color based on what the state of the particle is. We can perform an experiment where we can stream a whole bunch of particles from a reservoir and write down what the properties are. After doing this for 1,000,000 particles, we notice that half are red and the other half are blue. What does this say about the reservoir? Was every particle in a quantum superposition of red and blue? Or was there just a classical mixture of 500,000 red particles and 500,000 blue particles being spat out at random by the reservoir? To answer this question, we need a special setting on the box. Say there's a switch that sets the basis of the measurement. It can switch between the red-blue basis or the green-yellow basis. Green and yellow are defined as specific superpositions of red and blue. If we measure 1,000,000 more particles again, but this time in the green-yellow basis, and all of them were found to be green, then from these four probabilities, we can confidently state that all the particles were in a state green, that is, in this particular superposition of red and blue. Note that there is nothing sacred about the RB basis over the GY basis. If we prepared 1,000,000 red state particles, then they would give a definite result in the RB basis and a 50-50 result in the green-yellow basis. But what if the particles gave random measurements in both the RB basis and the GY basis? Does this mean that the reservoir was indeed a classical mixture? Not quite, as we still have to check for a certain other possible superposition state that isn't covered by these basis settings. To understand superposition, we are going to have to run headfirst into the measurement problem. For quantum mechanics to predict results accurately, it requires that all measurements, i.e. all interactions with macroscopic objects, necessarily change the quantum state of the object to conform with the outcome of the measurement, that is, interaction. Consider a different, less abstract system. Photons and the Mach-Zehnder interferometer, named after Mach and Zehnder. A photon, that is a quantum of light incident on a partially polished, half-reflecting mirror called a beam splitter, has a 50-50 chance of either reflecting or transmitting straight through. We can verify this by shooting 1,000,000 photons one by one at the beam splitter and counting the number that end up in each path. Let us label these paths Path A and Path B. Now when a single photon hits the beam splitter, is it in a superposition of both paths, or does it actually decide to go one way half the time and the other way the other half of the time? Photons can only be detected in one of these paths at a time, as photons cannot split into two detectable half photons, which is how we know they are photons. So this measurement doesn't seem to support the latter hypothesis. But remember, whatever the quantum state of the photon is after it hits the beam splitter, the state gets altered to conform to one of the outcomes of the measurement. Since the measurement asks are you in path A or path B, every photon has to respond with one or the other answer. It has no way of conveying its superpositionness to this measurement. Naturally, we need to try and measure the photon in a different basis to resolve this issue. It turns out that beam splitters perform a very simple unitary operation on the photon. More on this later. You can combine paths A and B on a second beam splitter with outcome paths C and D, and this new setup can measure superposition. If the photon were in the A plus B superposition state, it would exit in path C. And if it were in the A minus B state, it would exit in path D. We can now actually change the sign by introducing a path delay in one of the two arms by moving this corner cube. The position of the corner cube can completely flip whether any photons entering this device will exit via path C or path D. We can set the interferometer in such a configuration that 1,000,000 photons going in will all exit in C and none in D. But this device only works if we do not measure which internal path the photons are taking. We just cannot ask the photons, are you in path A or path B, as if asked, the photon will be forced to reveal an answer and then conform to the answer, thus destroying the interference. The question, are you in path A or path B, and the question, are you exiting from path C or path D, are mutually incompatible and cannot be asked simultaneously. To see how this works, say we introduce a beam block in path A and repeat the experiment with 1,000,000 photons. Then we'd observe that 500,000 photons fall on the beam block, since the first beam splitter is a 50-50 beam splitter, and of the remaining 500,000 that took path B, half, that is 250,000, will end up in path C and the rest in path D, since the second beam splitter is also a 50-50 beam splitter. Blocking path A seems to destroy the interference. That's because blocking path A is a measurement. It asks the question, are you in path A? The photons that took path A obviously hit the beam block and answered, well, yes, I am in path A to this question. But what about the photons that took path B? Half of them seem to go out in path C and the rest go out in path D, even though in the absence of the beam block they all go through path C. How did these path B photons that ended up in path D even know that path A was being blocked if they didn't take path A? Don't believe me? Well, here's a video recording of an actual experiment. Okay. So here we have a polarization interferometer setup, and I'll explain the components in sequence. So, to start with, we have prepared a linearly polarized beam of light. So this beam is diagonally polarized and it's entering a calcite crystal. Now the crystal is oriented such that it can split this beam into two beams, one of which is horizontally polarized and the other one is vertically polarized. Now these two beams are of equal intensity, and they enter a halfway plate. The halfway plate rotates the polarizations by 90 degrees. So it changes the vertically polarized beam into horizontally polarized beam and vice versa. But we still have two beams. Now these two beams are entering a second calcite crystal, which is oriented such that it combines these two beams into a single beam again. The polarization state of this beam actually depends on the difference in the path lengths of these two paths. Right. To demonstrate that, we will use a third calcite crystal, which is oriented such that it can split this beam into its diagonal and its anti-diagonal components. We're using a lens to further spatially separate its outputs, but I shall refer to these as outputs 1 and output 2, and one of these are diagonally polarized and the other one is anti-diagonally polarized. Now, we can actually affect the path length difference for these two beams by tilting the second calcite. And when we do that, we will notice a change in the amount of light in the diagonal versus the anti-diagonal outputs of this entire setup, vis-a-vis outputs 1 and 2. So there's a knob here that can rotate this calcite, and as I do that, you will notice that I can completely eliminate one of the outputs or the other. Right. So I can choose an orientation for the second calcite crystal such that the combined beam at its exit can be fully diagonal or fully anti-diagonal. So I'm just going to orient it such that it's all coming out of a single output. So now to demonstrate superposition, we had to focus on what is going on here and use the photon picture of light. So if you believe that light is composed of photons, then classically you would assume that the photons have a 50% chance of going into one of these paths and a 50% chance of going into the other one, right? However, every single photon that enters this setup right now knows to end up at output 2, right? And they just know to avoid output 1. But if I now block one of these paths in between the first and the second calcites, you should notice something interesting. You will see that both outputs 1 and 2 have some photons in them. So as I block and unblock the path, you can see the difference. The same is true if I block the other path. It somehow makes output 1 a valid option. Now, this is strange if you believe that photons are classical particles. That is, that they take one of these paths but not the other with 50% probability. However, when I block one of these paths, the photons that didn't take that path somehow know to end up in output 1. Right? So when both paths are unblocked, every single photon that goes through ends up in output 2. However, when I block one of these paths, some photons actually do end up in output 1. Now the question is, how are those photons aware that this path was blocked when they didn't take it? Right? The resolution is, of course, that every single photon that enters the first calcite is in a quantum superposition of both these paths. Right? It's not the case that they take one or the other with half chance. Every single one is in both these paths. Right? So when I block one of these paths, half of them are lost because they hit the card, and the others that go through are actually aware that that path has been blocked, because technically they had some quantum amplitude in that path as well. And that is how their output probabilities change at the end of the setup. Right? And that is a strong argument for superposition. And that's your interferometer. Superposition is a fine way of explaining a lot of experiments, but why is it so strange? Why do we only observe it in small objects under controlled conditions? Why isn't my toast, say, in a quantum superposition of done and burnt crisp? The trouble with cats and toast is that they are massive. Massive objects are always interacting with their macroscopic environment. That is, they're always being measured. A cat is exchanging heat and gases with the atmosphere in the box and the box itself. It is exciting acoustic or sound modes in the atoms of the box floor and moving air molecules about just by breathing, like I'm doing right now. Even if we were able to prepare a cat in a superposition of alive and dead, whatever that might mean, the universe is constantly measuring it, asking the question, are you alive or are you dead? A cat in mortal danger will continuously answer it, whether or not we open the box to take a peek.